All right, so today we're going to take a look at reasoning and logic, and again, some of these pieces are going to be familiar ideas to you, and others of them might not. Are you okay?
I wrote her own notes.
I'm sorry.
It's okay. She was just making fun because
she was so proud of herself for putting off her notes.
I printed off the notes on time. That's wrong.
You'll be all right. You'll be all right. You took it to bring up a piece of your life. All right, so the first thing I want to talk about is a statement. A statement is simply a sentence that's true or false. And so I ate cereal for breakfast would be a statement. What did I eat for breakfast would not be a question, right? It's neither true nor false. It has some other kind of an answer. Another item that's not a statement would be a command. Like if I told you, get out your notebooks. That's not a true or false thing, right? That's a command. So statements are what we're going to be basing all of our logic arguments on. A negation for a statement is simply not P. Sometimes it's very straightforward, like this one. I ate cereal for breakfast. The negation is I did not eat cereal for breakfast. The negation is not I ate waffles for breakfast. Okay? Right? Because that means I didn't eat cereal, but it doesn't mean I didn't have oatmeal or I guess we eat cereal. How about pancakes or eggs or whatever? Okay, so you have to have the exact opposite for it to be negation. The problem comes in with when you have certain words in a statement called quantifiers. So if you have universal quantifiers or existential quantifiers in a statement, it's tricky to do the negation. So an example of a universal quantifier is when you have words like all, or every, or no. It means something that's included among the entire group. For instance, if I said we have no boys in this classroom, right? No. There's none of you are boys. Okay. There's an example there also. All people are sinners. That word all is applied to everything else in the sentence. Existential quantifiers mean there exists one or some or whatever. So it refers to one or more elements in the set. So some cats go to heaven. I had one class last semester that I could not have said all of the students were girls because I had exactly one boy. All it took was one, right, to make that statement false. Right? So when you create negations, the quantifiers present require you to be much more careful in how you change the sentence into a negation. So we're going to take an example and we're going to do that. So we're going to do all dogs go to heaven. It's in the movie Way Before Doll's Time. So the way that you change a statement into its negation is you take a look at those quantifiers. So this quantifier right here is the word all. And we take that quantifier and we turn it into the other kind of quantifier. So the word all is a universal quantifier. So I need to take the word all and turn it into an existential quantifier. So that means I could change it to the word some. I could change it to the phrase at least one or there exists. Any of those would be sufficient to change it to, right? I could do that. So I'm going to do at least one for no particular reason. So what would I need to have happen to negate the statement, all dogs go to heaven? Well, I would need at least one dog to not go to heaven. And the opposite in this quantifying sentence is not go to hell. Okay? Don't go inferring things that are not there. You change what's there verbatim. Okay? So we're going to say at least one dog does not go to heaven. Okay, so all turns into at least one. Or you could say something like, some dogs do not go to heaven. Or there exists a dog that does not go to heaven. Any of those would work. All right, now we see the other quantifier in part B, right? We see the word some. The word some is an existential quantifier. So I need to change this existential quantifier into a universal quantifier, which means I need to change the word some either into the words all, or for every, or none, something that applies to everything else after the sentence. Now, you also have to change the rest of the sentence. So the rest of the sentence says that you've got some hard classes, right? It says some of my classes this semester are hard. So you have sort of two things you need to think about. You can either change this to say all of my classes are hard or none of my classes are hard. One of them is correct and one of them is not. So I'm going to write both of them down, and I want you to think as you write down which one really is the opposite of this statement. Because if I had all of my classes that were hard, then certainly some of them would be, right? Some of them, namely all of them. So all of my classes are hard is sort of a more drastic statement than what I had, but it's not the opposite statement of what I had. Make sense? Now, you also could do this one other way. So let me write this, although I don't think this is quite as natural. There is one other option. You could change the word some into all. Use green. I could write all. But if I wanted to use the word all, and I was emphatic about wanting to use the word all, I would have to do something like this. All of my classes this semester are not hard. Notice I did not say easy. Okay? There's somewhere in between hard and easy. You guys know it. Right? There's classes that you work hard in, but they're not conceptually hard, and you got to make those distinctions. So we're not trying to do that. We're just trying to negate what's simply said. So you could say all of my classes this semester are not hard. It is not quite as clean, right? But it's correct, and either of those statements at the end would work just fine. Sound good? All right. Truth tables. Some of you thought you were never seeing those again, didn't you? All right. So a truth table is a diagram. And you've been doing some diagrams and problem solving sections so far, right? It's a diagram that allows you to analyze components of statements. That's what it does. Okay. So if you have a statement, so let's say we have a statement P. The first thing, this happened on an earlier slide, although I didn't really make note of it, but hopefully you read it. The negation is a tilde and then a P. And if we create a truth table, it looks like a T-bar, something like that. It's like two columns. Okay. The statement itself goes in one column, P. And whatever the statement is, remember we said statements are things that are either true or false, and those are my only choices. So I have one option that this statement is true. I have another option that this statement is false. Those are the only choices. Okay. Then, if I were to consider that compared to its negation, well, if the original statement is true, then the negation is false. And if the original statement is false, then its negation is true. Okay, we're taking baby steps. We're going to add to this diagram with the next slide. But before I get there, I need to see how we would combine two statements. So if you had two statements, we're going to represent them with letters, right? Our statement is going to be P, and we can have another statement, Q, and don't ask me why P and Q is always Q, so I don't know. I wrote both P's, P and Q. And then if you have a third statement, you're going to see an R in there. So you have two statements, P and Q. And then if you join them with connectives, such as and, or if then, which are the three most common ones, you form a compound statement. So something like, I teach math and I have children. Okay, those are two statements. One of them may be true, the other one may be true, they may be both true, they may be both false. There's two separate statements in what I said. and I joined them with a connected and. I could have joined them with the connected or. I teach math or I have children. I could join them with a connected if then. If I teach math, then I have children. Which doesn't really work, right? It doesn't work in the logic for it, but I can still create the sentence to say that. Right? So those are the three different kinds of connectives that we're talking about here. The first one is a conjunction, and that's the or. I'm sorry, it's the and. Get the right one in there. It's the and. So this is the first one that I gave you, where I said, I teach math and I have children. So you put the word and in between two statements, and you have a conjunction. And I want to show you what a truth table looks like for that. So allow yourself enough space, because you need to have 4 items written underneath each of your column headers. We're taking two statements, P and Q, and we're going to put the word and between. The symbol for the word and is an upside down V. Okay, so this says P and Q. That's what that symbol says. And. Okay, everybody with me so far? Okay. So one possibility is that each of those statements, me teaching math and me having kids, are both true statements. That is one option. It's equally likely, or at least an equal option, that the first statement's true and the second statement's false. A third possibility is that my first statement was false and my second statement was true. And what's my last option? False. They're both false. Now, I will tell you that no matter what happens, these are the only 4 options. So a lot of times when you're starting to work with these truth tables, you just know you're going to go TTFF, TFGF. Right? This is the pattern, it's always there. Okay. Now what we're going to do is we're going to create an and statement. So I'm going to do a third column, and I'm going to have the and symbol between them. So what you want to do is you want to decide if the compound statement, the and Q, is true. So if statement number 1 is true and statement number 2 is true, is it true if you combine them with the word and? Yes. So this is a true statement. So if it's true that I teach math and it's true that I have children, and I say I teach math and I have children, then that statement would be true as well, because each of the individual statements is true. Okay? So let's take let me take my second column or second row, and I'll talk about a colleague of mine. So I have a colleague who teaches math in the math department. Her name is Dr. Marsh. So you've met Dr. Marsh. Dr. Marsh does not have children, okay, but she does teach math. So if she came in and she made the statement, I teach math and I have children, would that be a true statement? No, because she doesn't teach math and have children. She doesn't have both of those things true at the same time. So her saying that statement would make that statement false. Okay. Third row, I have a sister. My sister is a dental hygienist. She does not teach math, but she has 3 wonderful children. Well, she has 3 children. So when we're looking at this third statement, if she comes into your classroom and she says, I teach math and I have children, would that be true? No, because she doesn't teach math. So this would be a false statement. Let's see. Let's say that my husband comes in. He'll work as no, he won't work as he didn't have he didn't have. Let's take one of you guys as an example. Megan comes in. She stands up in class because she wants to talk to you, and she says, "I teach math and I have children." Well, she doesn't teach math, right? Not yet. Someday she might. She doesn't have any children. It's not that I know of. Never. No, not right now. So no math, no children. So would it be true for her to come and say, "I teach math and I have kids"? Alright, so this would be false as well. Alright, so this is how you would construct a conjunction. Now, so I used examples as we went along for how to think about what these are. But if you take a look at what's going on, in order to have an and statement true, both of the component statements have to be true. If you have a false in either one of the component statements, then the compound statement can't be true. Okay. Now we're going to do disjunction. Disjunction has the word or in it. And the symbol for the word or is actually a V. So this is read P or Q. And we're going to create a very similar kind of diagram. It's going to have the same P and the same Q. It's going to have the same T, T, F, F, and the same TF, TF that I had before. And then I'm going to have my disjunction here, P or Q. Alrighty. So now I come into you, me, the one who teaches math and has children. And I say to you, I teach math or I have children. Well, I teach math, I have children. So if I put the word or between, and I say I teach math or I have children, that's true. I happen to have both. Both those things going on in my life. But if I put the word or in between, we are using what we call an inclusive or. That means both statements can be true and the compound statement is true. We're not using the exclusive or, which means it's one or the other or method. You can't do, we're not doing that. Okay? So if either of those statements are true, then with the or between, I teach math or I have children, and you'd say, that's true. Okay? So that's a true statement. So Dr. Marsh, she comes back in and she says, I teach math or I have children. And then is the statement true? Yes, it is, because she teaches math. Right? My sister comes back in and she says, I teach math or I have children. And the statement is true still, because she has the children, right? And then we'll pick on Megan again. And Megan gets back up and she says, I teach math or I have children. And the statement is false, because neither of those component statements have truth to them at the moment. All right, so when we're taking a look at a disjunction, the only time that I get a false statement is when both individual statements are false. Okay, everybody good with that? All right. We're going to do an example. We're going to create a truth table for P and tilde Q. So, truth tables always start the same way, and in some of the problems in your book, they start them for you with some columns, but they always start with the columns P and Q. And just so that we're all on the same page, because it makes it easier for me to interpret your work, if everybody will always do in the same pattern, it'll match the pattern of the book as well, so it'll make it easier for you to check your work. You'll do 2 T's, and then 2 F's, and then you're going to do T, F, T, and F. And even if you can't do anything else in a truth table, you're going to have that part of the pattern, because it's always the same. Okay? That's always good, isn't it? It's like when you were in geometry and somebody said to you, you can always start a proof. The very first part of the proof is you write down the given information, right? This is the given information for this argument. All right, the next thing you do is you look at what you're trying to create the truth table for. I already have a column for P, so I don't need to mess with him. But I don't right now have a column for tilde Q, correct? So I need one of those. So I'm going to create a column that's got a tilde Q in it. And then I'm going to fill that tilde Q column in. Well, that tilde Q means negation of Q. And I already have a column for Q. So I use my column for Q and I go down piece by piece. So if Q is true, then tilde Q is false. If Q is false, tilde Q is true. And then if it's true, it's false. And if the original one's false, then it's true. So there's tilde Q. Now each of the individual component statements in this conjunction are in my table. I have P in my table, I have tilde Q in my table, which means my last column that I need to create is the P and tilde Q column. And what I will do is I will look only at the column P and at the column tilde Q as I make my comparisons. So looking at those two columns, I have a T and I have an F, and I have an AND statement. Right? That's AND. So if I have a T statement, a true statement, and a false statement, and I do an AND between them, is that result true or false? It is false. If I have a true statement and a true statement, is that result true or false? True. If I have two false statements, false. If I have a false statement and a true statement, false. And that is my truth table finished. Now that's a little bit different than the next question. The next question does not say create a truth table. What does it ask you? It asks you for a truth value. Not only that, it gives you some information that the first example on this page did not. It tells you what P and Q are, doesn't it? So I don't have to create a whole table. I only need one row of my table. I need the row specifically where I have P is false and Q is true. So basically what I'm going to create, I'm going to create a one row truth table. Okay? So my truth table, again, is going to have a P and a Q in it because they always have P's and Q's in them, no matter what size or anything. We got P and Q. I'll fill in some other details about the T's and F's in a moment. But if you take a look, I don't actually have P or Q in this compound statement. I have a tilde P, so I'm going to need that one. I have a tilde Q, so I'm going to need that as well. And then I need to join it all together, which is the last column, which is tilde P or tilde Q. We understand all the column letters. Okay. Now, it actually told me that P was what? False. So I only need to have one option underneath P, false. And it told me that Q was true. So again, I only need one option underneath Q. And then we will create everything else based on those pieces of information. So if P is false, then tilde P is true. And if Q is true, then tilde Q is false. Now this last column only refers back to these columns before, so I'm only looking at these two for the conjunction statement at the end. Sorry, the disjunctive statement at the end. T and an F, and I have the word or between them. True. That is a true result. A true or false statement becomes true. Now, you have to be careful because you created all of the work that you haven't answered the question. The question asked, what is the truth value? And the answer is true, because my last T here is my answer. So the truth value is that it is true. All right. The next slide is the slide that is off of what your notes may be. So does your slide look like this? If your slide doesn't look like this, it just has example 4 on the next slide. Yeah. All right, so two statements are logically equivalent if they have the same truth value in every possible situation. Okay. And that is written P with a triple sort of equal sign, it looks like, 3 horizontal lines between the Q. And we're going to run into some logically equivalent arguments later on, but I'll show you that when we get there. Maybe on the next slide. De Morgan's laws are a way to negate compound statements. So take a look. If you have a P and Q statement that you want to negate, put the negation sign between them. It is equivalent, logically equivalent, to use that negation in front of P and that negation in front of Q separately. And then what happens to this and statement? It becomes an or statement. So I'm going to use an example with you again, the same one I used before. I teach math and I have children. What does it take to make that statement false? Well, it takes either one of those individual statements being false. Right? So you can negate the first one, or you can negate the second one, and the whole thing is false part. Right? This is what I'm doing when I'm sitting up here trying to create examples for you, right? In my head, I'm trying to think, how do I negate someone who is teaching math and does not have children? How do I negate someone who is not teaching math and does have children? Right? I had to negate one piece or the other one. The second one of De Morgan's laws, a negation of an or statement. And we didn't do an example of an or statement with this, but if you negate the or statement, the same process works, right? I can negate either piece, and the or statement becomes an and statement. So the first De Morgan's law example we're going to do is simply a symbolic example. If I have the statement P and tilde Q, and I want to negate it, what will I get? So I negate the first piece, so what will that look like? Tilde P. I negate the and symbol, so it becomes an or symbol. And I negate tilde Q, so it becomes Q. You don't have two tildes. It would be like saying negative, negative 5. We don't do that, right? Same thing here. So de Morgan's law will allow us to write the negation in a much more concise form. Agree? The second one would be easier to do than the first one if I was doing truth table on it. Which is exactly what we're going to do. That's exciting. We're going to create a truth table. We're going to create a truth table both for tilde P and tilde Q, which is apparently running into other things. And we're going to create a truth table for the answer that we got from the previous slide. Okay? So you probably want to use the space that you've got there and then the space over the side for the two separate truth tables, right? So here's my first truth table. My first truth table is going to look exactly like that statement. So I need a P column, I need a Q column, and then if you take a look, we do inside of parentheses, just like in algebra, and then we move out. So inside the parentheses, you see we've got a tilde Q, so I need a tilde Q. And then inside the parentheses, I have the conjunction, P and tilde Q. And then after I do that, I can move outwards and I've got the negation of P and tilde Q. Those are my column letters. All right, so what goes in the P column? True, true, false, false. What goes in the Q column? True, false, true, false. What goes in the tilde Q column? Right, false, true, false, true. So far that's exactly like every of those we've done, right? And then had a negation to do. Now I need to compare P and tilde Q. So here's P, and here's tilde Q. So these are the columns I'm comparing. And I have an and statement to make with them, rather. So the first one I've got T and F, that's false. The next one I have T and T, true, not dynamite. False and false, that's false. F and T, that's false. And then the last column says tilde in front of it. So it's just the opposite of the column I just created, right? I just change every T to F and every F to T. So this becomes T, F, T, T. Okay, everybody good with that? We're going to compare that to another truth table. So I need more space. So this is my other side of my page that you're working on. I need, again, a P and a Q, and then what was that? What did I have over here? Let's see. My negation from the page before looked like this. It had tilde P or Q, right? Okay, so that's what I'm creating now. So I've got a P, I've got a Q. What else do I need? Tilde P, and then the total of all of it, right? Tilde P or Q. Okay, so what goes in the P column? True, true, false, false. What goes in the Q column? True, false, true, false. What goes in the tilde Q column? Sorry, tilde P column. False, false, true, true. Then I want to compare the tilde P column with the Q column to create an OR statement, right? True and false create an OR statement. True. T and F is true for an OR. How about F and F? That's false. How about TT? That's true. How about FT? That's true. And what you're wanting to do is you're wanting to compare this ordered list with this ordered list. And if you did the negation correctly and you made your truth tables, you did those correctly, those lists should be identical. And are they? Yes, they are. All right, one more we're going to do with De Morgan's Law is using it to rewrite a statement. Okay, so I kind of gave you a little bit of how I was thinking with De Morgan's Laws to create my statements. This statement, again, this is a correction as well. This is the other correction. So if you printed yours out with example 4, up high, not up high, whatever, change it. It should say, it is not sunny and I will go for a walk. Okay? So please make the corrections. I had some line lapse when I was originally writing it down. This is correct. All right, so De Morgan's Laws, I have an and in between. So I negate each statement individually. So what would I do to negate it is not sunny? It is sunny. What would I do to negate and? I would put an or. And what would I do to negate I will go for a walk? I will not go for a walk. So it is sunny or I will not go for a walk is the negation of the statement. It is not sunny and I will go for a walk. And I think that's actually a really good spot for us to stop on.